Good morning. Today I'm going to talk about the different layers and characteristics of the sun's atmosphere. So, when we talked about the surface of the sun, we said that was called the photosphere. And the photosphere is about 6,000 degrees Kelvin, and right above that is the chromosphere. Now, the chromosphere is the start of the sun's atmosphere. And we're going to see that there's many layers to it, but this is like the bottom layer of the sun's atmosphere. And when you look at it compared to some of the other features, the chromosphere is actually pretty small. It doesn't rise up above the photosphere by very much. Maybe a couple thousand kilometers, which for the sun is actually really small. And you can really see it in this image here. In this image, during an eclipse, you see this ring of red around the sun, and that ring is very close to the surface of the sun. Well, that ring of red is the chromosphere. And what we're seeing are hot gases that are, and the gases are mainly hydrogen. Remember, hydrogen makes up most of the sun. But it's these really hot, intense gases that are giving off this light. Another thing that's kind of unusual with the chromosphere is that it's hotter than the surface of the sun, the photosphere. So I said the photosphere was maybe about 6,000 degrees Kelvin, where the chromosphere might be around 10,000 degrees Kelvin. So not a lot hotter, but noticeably hotter. Like, we can measure it as being several thousand degrees warmer, which is weird because the source of heat is the core of the sun, and that heat then radiates out from the core, right? So we've got something that's further away from the core, but it's actually hotter. So now let's take a look at the next area of the atmosphere. And what we see here, we'll see a similar image with a eclipse, but the next area is the corona, and it is much larger than the chromosphere. The chromosphere, we said, was really small, right? Like, didn't extend very high up into the atmosphere, where the corona can extend millions of kilometers up above the surface of the sun. And you can see this. Remember, the sun is huge, so millions of kilometers doesn't have the same feel as what millions of kilometers would be comparing the size of the Earth, because the Earth is something like 8,000 kilometers in diameter and not very big. But in this image, you see the corona go way up over the surface. It's this bright haze, this bright glare, all the way around the sun that's extending away from the sun. Much, much bigger. The corona gets really weird, though, because it is unusually hot. And by unusually hot, I mean we're talking 1,000,000 degrees here. So we went from the surface of the sun at a few thousand degrees, right? Like 5,000, 6,000 degrees Kelvin, to now we're in the corona, which is this flaring hot gas moving. And you even get to this point where it's not even hot gases as much as it is these charged particles coming away from the sun, but has a temperature of 1,000,000 degrees or more. And this is still an active area of research. But it appears to be that there's some kind of transference of heat from the sun to the corona because of an interaction with the sun's magnetic field. And the sun's magnetic field is very wild and erratic and twisted. And there's something going on there with that interaction that's causing this really high temperature. Again, this is still something that is being studied. The answers are not all in, and it's an area of active research. All right, now we want to talk about the solar wind. So I said that there were charged particles coming out of the sun. Well, these charged particles stream out at a very rapid rate, and they emanate into space. They just like the light from the sun, it just moves out and propagates through space away from the sun. And in this picture up here, we see the charged particles streaming out from the sun and making their way to Earth. That's what you're seeing in this image here, is the charged particles coming right at Earth. But Earth has this blue field in this image. This is Earth's magnetic field, so the North and South Pole. And this magnetic field can actually protect Earth from these charged particles, which is very important, because if these charged particles just hit Earth without any kind of deflection, this is cosmic radiation. This would be very harmful to life on Earth. So Earth's magnetic field is able to deflect the solar wind. Now, when it does that, some of these charged particles, you don't see it in this image up here, this diagram, but some of these charged particles will stream down straight on top of the North Pole or straight on top of the South Pole. So they'll ride these field lines down and hit at the North and South Pole. So what does that mean? Well, when it does that, these charged particles that were deflected down there can actually interact with our atmosphere and the gases in our atmosphere, and they make them glow. So at the North and South Pole, on occasion, when you get a lot of these charged particles streaming down, you see the aurora. And in the north, it's the aurora borealis. And what that is, again, is gases in our atmosphere that are being excited, given energy, and they glow as those streamed particles come down. All right, I hope this helps. Thanks.